Hi there, welcome to Raylene Maths. This is Raylene, and today we're going to take a look at quadratic functions. We're going to start by looking at a pattern of growing blocks. So we've got a couple of different case numbers. We've got the first picture, or the first case, the second case, the third, and the fourth, and so on. And we're going to consider how many blocks we have in each picture. Well, we can start off counting pretty easily. We see that we've got one block, then we have four, and then we count them all up, we get 9. And here we can count them again. Takes a little bit longer, and we can see it'll get longer as the pictures continue, but here we have 16 blocks. And so we want to consider drawing the fifth picture. Well, we can do that by considering how the blocks are growing. We might consider that we add another row, so we duplicate the bottom row and then we put a block on either end, or we might consider pulling apart the center and triplicating the center row, or the center column, and then putting an extra block on the top of the center. But ultimately, there are different ways that we can see how the blocks are growing and come up with a pattern. If we wanted to count blocks for bigger picture numbers, there are a couple of ways we could do this, but one might be to reorganize how these blocks look, rearrange them. And so I'm just going to take this, flip it here, and then see that that grouping of blocks can fit just right here. And now, because of the way it's been organized, it's a lot easier to count because I have a 4 by 4 square. And indeed, 4 squared is 16. So that helps us to come up with the fifth picture and to see how the blocks are growing much more easily. So here's my fifth picture. I'll just number these again and come up with the number of blocks in each case. So we have 1, 2, 3, 4, 5, and then we have the squares of those numbers, 1, 4, 9, 16, 25, etc. So from there we can see how many blocks there are in the fifth picture. Are 5 squared equal to 25. In the 10th picture we would have 10 squared equal to 100 blocks, and in the 200th picture we would have 200 squared, which is 40,000 blocks. So it's interesting to be able to predict what happens in the nth case, but it's also interesting to see the pattern between these numbers. And so one thing we're going to consider is the case number or the picture number increases by 1. In other words, as the length of the square increases by 1, what's happening to the area? So we might consider that we had a square of 3 by 3 here, if we took these blocks and put them up here. And so the length is really the picture number. I'm just going to call that L for length. And then the area, maybe I'll write the word above here, is the number of blocks. And so this is a very geometric interpretation. And we can see that we have an increase of 3 blocks going from the first case to the second case. From the second case to the third case, we've added 5 blocks. Now this is really just corresponding to the bottom row. If we take this 2 rows and shift it up, we add another row of 5 blocks. We take that figure and shift it up, we add a row of 5 plus 1 plus 1,
second
or 5
difference
plus 7
in
blocks.
the blocks. So
And
we
on
have
and on it
a
goes,
first difference, which is the
and
black
we can just
numbers,
get this
which
general
is a changing
pattern here.
difference.
Now, if this
but then the
relationship between these
numbers
two
is a
quantities,
constant
this input
second
and this
difference.
output, if it were linear, then this difference would be constant as the change in the input is constant. But we don't have a constant difference here. In fact, we can take a second difference and we would add 2 to 3 to get 5. In other words, 5 minus 3 is 2. 7 minus 5 is 2. And 9 minus 7 is 2. And on this pattern goes, and we see that the second time we take a difference, we get a constant. This number pattern is the hallmark of quadratic functions. So if we come over to Desmos and plot our tables of values, we can see the x represents the picture number, or now we see it's the length of the square, and y or y1 represents the number of blocks in each picture, or the area of the square. And so if I just turn on the data for x and y, we see that we've got these points that are forming a parabola shape, half of a parabola shape. Now I've got 2 other columns here. I'm not going to turn on these as tables of values, but I just want to record the difference, the first difference and the second difference from the y1 to y2 values, or consecutive y values. In other words, 4 minus 1 is 3, 9 minus 4 is 5, and I could read this table as 1 plus 3 equals 4, 4 plus 5 equals 9, 9 plus 7 equals 16, and so on. So with that in mind, I can see that 81 plus 19 is 100. Then if I knew what this next difference would be, I'd be able to find out the next perfect square. Well, I know that each of these first differences in y, or area of consecutive pictures of squares, is increasing by 2 because that's the second constant difference. And so from here, we're going to take a look at adding another 2, so 19 plus 2 gives me 21, and then 100 plus 21 is 121, and 121 is indeed 11 squared. So we can generate more values in the table by understanding this first difference column and the second difference column. Let's just take a look to see how these number patterns actually play out on the graph into the geometry. So we're really making a link between the numerical and the algebraic and the graphical and the verbal, what the description is of this graph. So here we have our graph, and we can see I've plotted a few points, 7, 49, 8, 64, and so on. And we can see that as x increases by 1, we have first of all a height increase of 3, then a height increase of 5, and a height increase of 7. By the time we're going from the point 749 to the point 8, 64, we have a width or a run increase of 1 and a height or a rise increase of 15. And it changes as we go on. If we were to connect with a slant line segment, we could form a right triangle here, and we can see that these right triangles have different heights over bases, and therefore we don't have similar triangles and we don't have a constant slope. But what we do see again is that the height of 3 to 5, from 5 to 7, from 7 to 9, and so on is increasing by 2 every time. And again, this is the hallmark of being a quadratic function, that the second difference is constant. Now, we do have a relationship from x to y. We know that y is equal to the area of a square whose length is x, so y is equal to x squared. But we can also see how to get these first difference values, 3, 5, 7, 9, etc., from the x values. In fact, if we take each of these x values and double them and add 1, for example, 2 times 8 is 16 plus 1 is 17, or 2 times 5 is 10 plus 1 is 11, we get that the first difference column is going to be 2x plus 1. And so let's take a look geometrically where this is coming from. If we take our square of length x, and then we increase the square by 1, which means that we're going from one square in the sequence of pictures to the next one up, we have that the length goes from x to x plus 1. Similarly then, the area goes from x squared to x plus 1 all squared. And if we expand this, we're going to get x squared plus 2x plus 1. And we see that the x squared, first of all, was the area of the previous square, and then the 2x plus 1 is the difference or the change, or in this case, the increase from the area from the first square or the previous square to the current square. In other words, all of the shaded area has an amount of 2x plus 1, and that's what's indicated here by this column, this 2x plus 1. Now that we have a pretty good understanding of the number pattern behind quadratic relationships, we're going to look at quadratic functions and their characteristics. A quadratic function is a second-degree polynomial, and it has the form in standard form of y equals ax squared plus bx plus c. Now the condition that a is not 0 is important because if a were 0, this equation would simplify to a linear equation, and we would end up having the graph of a line, where the slope would be b and the y-intercept would be c. But as long as a is non-zero, either positive or negative, the graph of a quadratic function is called a parabola. Now the parent function has an a value of positive 1, and we have a concave up parabola. But if a is negative, we would have a concave down parabola. Quadratics are the simplest of all nonlinear functions, which are functions that have a constant slope. So this is the simplest of all nonlinear functions. And because there are no values that cannot be squared or multiplied by constants and coefficients a, b, c, there is no restriction on the domain. So the domain of a parabola is all real numbers. In other words, this graph goes forever to the right or to the left without any breaks, gaps, or other discontinuities that we may discuss later on. The degree of a quadratic polynomial is 2. Again, that's because the highest exponent on x is 2 in the expanded version of the equation. And related to the degree of the polynomial, we have the maximum number of x-intercepts is the same as the degree of the polynomial. That doesn't mean we always have 2 x-intercepts for a parabola, but we can't have any more than 2. And for all polynomials, we will see that the maximum number of turning points is 1 less than the degree. And in this case, the number of turning points, maximum number of turning points for a parabola is 1. And indeed, we have exactly 1 turning point for a parabola. We have an axis of symmetry for all parabolas that pass right through the vertex, and in the case of the parent function, the axis of symmetry is also the y-axis. So this actually tells us that the parent graph has even symmetry. And lastly, we'll talk about the end behavior or the zoomed out behavior. So the zoomed out behavior talks about as x approaches negative infinity on the left or as x approaches positive infinity on the right. For a concave up parabola, when a is positive, as x goes to the left or to the right, y will go up. And that's indicated by this set of limit notation or approaching behaviors here. But for a concave down parabola, as x goes to the left, y goes down, and as x goes to the right, y goes down. So for a polynomial of even degree, the two ends will either both go up or both go down. So here we have some of the key features written in different forms about the domain, the symmetry, the vertex, axis of symmetry, and the x and the y-intercepts. These are the key features that we will analyze for all parabolas. There are three forms that we can write the equation of a quadratic function in: standard form, vertex form, or factored form. And these three forms allow us to get all of the main features and the key points about the graph, as well as help us to solve for the x-intercepts of a quadratic equation. So the standard form is an expanded polynomial form, and we tend to put the leading term first. The vertex form is the only form where the variable x shows up only one time in the equation, and this allows us to see transformations, including the translations to get the new vertex at h, k. The factored form is a form where, if possible to factor, allows us to see that the x-intercepts would be r1 and r2 immediately. So without going through all of these different features, keep an eye out on this table for the different information, and we will just go through some exercises to see how we can convert between these different forms and take advantage of the way that the forms are written to get the important information to graph a parabola. Last thing to mention is that the only parameter, which is a non-x and y letter, that is in common for all three forms is the letter a. And so the values of a tell us different things about the parabola. First of all, we already spoke about a being equal to 0. If a is 0, then the graph is a line, not a parabola, and we would have a slope of b and a y-intercept at 0, c. So as long as a is not 0, we will have a parabola, and if a is positive, we have a concave up parabola, so the vertex is a minimum. And as x goes to the left or to the right, y goes up. But if a is less than 0, we have a vertically reflected parabola, a concave down parabola. The vertex hk is therefore a maximum, and as x goes to the left or to the right, y will go down. This is the end behavior we're talking about. Furthermore, if the absolute value of a is more than 1, that means that we are going to have a taller than parent parabola. In other words, the parabola we get will be taller, or the y-coordinates will be scaled more than the heights of the y-coordinates on the parent graph. And because the parabola is taller, the width actually seems to be decreased, so the parabola will look narrower than the parent parabola. And then if the absolute value of a is less than 1, between 0 and 1, then the parabola will be shorter because we will be multiplying the y-coordinates by a number that makes them smaller or closer to 0. And when we have the parabola looking shorter, it will appear wider than the parent parabola. Let's take a look at a practical example now where we're given a function in either the standard, the vertex, or the factored form, and then come up with all of the information about the parabola. The first two lines here represent the other two forms of the equation, whereas this down here, vertex, means the coordinates of the vertex point. So let's get started and see what we can fill in right away. Well, the domain, we know that the domain of all polynomials, all parabolas, is x contained in the reals. We also know that the parabola is going to be concave down because a is equal to -2, and therefore we're going to have a maximum for the vertex. And we also know that as x approaches negative infinity, y will approach negative infinity, and as x approaches positive infinity, y approaches negative infinity. So both of the ends go down as we go left or right on the graph. Then we can easily come up with the y-intercept because the y-intercept is, for any graph, not just a parabola, the y-coordinate when x is equal to 0. So we could write this as ordered pair notation as 0, f of 0, which is going to be 0, 10. And so this kind of reminds us how to get the x-intercept. We get the x-intercept by setting y equal to 0. And so we can set y equal to 0 from factored form. So I'm first of all going to factor this, call this y equals -2, and I see that there's a constant factor, or a common factor of negative 2. So I'll factor that out first. And then hopefully I can factor the quadratic, and in this case I can, as x plus 1 times x minus 5 times the negative 2. So we'll talk a little bit about the quadratic discriminant in another video to see how we can predict if a trinomial or a quadratic expression can be factored. Now, setting y equal to 0, we end up seeing that x is either going to be, well, first of all, we can divide both sides of the equation by negative 2. We could have done that as soon as we set y equal to 0, earlier or later. And now by the zero product property, we get x plus 1 equals 0, or x minus 5 equals 0, so x equals negative 1 or x equals 5. I'm just going to rewrite that here, so it says x minus 5 equal to 0 first, but you can go ahead and change it to solve for x in one step. So we've got the two x-intercepts, negative 1, 0, or 5, 0. We can plot those points, 0, 10, negative 1, 0, 5, 0. Now we can think about coming up with the vertex. The vertex is located at h, k. Once we know the value for h, we can substitute into the coordinate into the equation for x and solve for k. Now there's two ways we can work out h. From standard form, we can use the a and the b values to work out h, and so a is equal to negative 2 and b is equal to 8. So negative 8 divided by 2 times negative 2 is negative 8 over negative 4, which is 2. Or we also know by symmetry that the axis of symmetry, which is x equal to h, is the midpoint of the two x-intercepts. So I could also work out h as r1 plus r2 divided by 2, where r1 and r2 are the two x-intercept values that we solve for here, negative 1 or 5. So negative 1 plus 5 divided by 2 is 4 divided by 2, which is 2. So either way we do it, we get that h is equal to 2. So this is good news, and therefore we can work out k, which is going to be f of 2. So k is the specific letter used for the y-coordinate at the vertex, and h is the specific letter for the x-coordinate of the vertex. Now we can take the h or x-coordinate of the vertex and substitute it into either the standard form, the expanded or function form, or we could put it into the factored form. I'm just going to make note that we have the factored form here. Oh, and while I'm at it, rather than labeling it here and taking up some space, I can put it in its space over here. So the factored form is y equals negative 2 times x plus 1 times x minus 5. Now I personally prefer substituting into the factored form because it makes it a little bit easier to evaluate. Negative 2 times 2 plus 1 times 2 minus 5. And that's going to give us negative 2 times 3 times negative 3, which is going to be positive 2 times 9, which is positive 18. So now we know that the vertex is a maximum located at 2, 18, and because the parabola is concave down, we know that the range is going to be y less than or equal to the maximum y-coordinate. So the only thing left to do, apart from sketching the parabola, is to come up with the vertex form of the parabola. And the vertex form requires us to know h, k, which we do, as well as a, which we were given. And so y minus k is equal to a times x minus h all squared, gives us the vertex form of y minus 18 equals negative 2 times x minus 2 in brackets squared. So now we know everything there is to know about the parabola, and we can sketch the axis of symmetry and plot the vertex as well and come up with the sketch of the parabola. 16, 17, 18. Notice my grid here is 1, 2, 3, 4, so the grid is really quite tight. I have the axis of symmetry line. I'll draw it in a different color because it's not technically part of the graph. And while I'm at it, I'm going to label and put arrows on all of the axes. So label with x and y. And I also have a symmetric point, a mirror image point, at the same height as the y-intercept at a height of 10. I might as well plot that point. And that it's that symmetry which allows me to come up with the x equal to 2 value. I could have taken the x-coordinates for these 2 points and found the midpoint of them. 0 and 4 has a midpoint of x equal to 2. Just like I took the x-intercepts and found the midpoint of negative 1 and 5 and came up with x equal to 2. So it doesn't always just have to be the x-intercepts, but any 2 points that have the same y-coordinate, that are at the same height. You can average them to come up with the axis of symmetry for a parabola. And from here, I'm going to make sure that I sketch my parabola as a curve. It's not a line. We talked about how we don't have a constant slope for a parabola, and this parabola is the simplest of the nonlinear functions. So I got a parabola like that, and I filled in all the information. Basically, I can do any problem solving I want with this information and this sketch of a parabola. So for the remaining questions, there are quadratic functions given in different forms, either the vertex form or the factored form, and you just need to manipulate the forms to come up with all the information. So I encourage you to pause the video and to try it, and then to check the solutions yourself to see how you did. Okay, here's another parabola. This time we have x written only one time, so this is the vertex form, and immediately I'm just going to fill in what I can. I know the domain is all real numbers. I know that the vertex is going to be a minimum because my a value is equal to a positive 1 here, which means the graph is concave up. And I also know that the h comma k values are negative 2 comma negative 9. And I'm just going to write the word minimum here rather than circling it. I also know the axis of symmetry equation. It's x equal to h, which is negative 2. And I know the left-end behavior and the right-end behavior. As x goes to negative infinity, y is going to go to positive infinity, and the same on the other side of, on the other side of the graph. As x approaches positive infinity, y will also go up, approaching positive infinity. So I can come up with the range as well, because I know that the minimum y value is negative 9, and so y is going to be greater than or equal to negative 9, coming from the vertex. Now let's work out the y-intercept, and we do that by substituting x equal to 0. We can do it directly into this form without expanding. And so if we substitute x equal to 0, we have y plus 9 is equal to 0 plus 2, which is 2, and then squared. And so y is equal to 4 minus 9, which is negative 5. So we have the y-intercept located at 0 comma negative 5. We can plot some of this information. Negative 2 comma negative 9 for the vertex, and then 0 comma negative 5 for the y-intercept. We can also plot our axis of symmetry line, or axis, and we can come up with a symmetric point on the other side of the axis of symmetry at a height of negative 5. Now let's come up with the x-intercepts, and to do that we want to set y equal to 0. So we can come up with the x-intercepts directly from the vertex form. If we substitute y equal to 0, we get that 9 is equal to x plus 2 all squared. Now, rather than expanding this and introducing an x squared and an x term, we can simply take the square root of both sides. So keeping in mind this is just 9 on the right side. After we take the square root of 9 is just 3, and the square root of stuff squared is the absolute value of stuff. Now, from the perspective of one-dimensional distance, maybe you consider it as a circle with a center. We've got a center located at negative 2 along the x-axis, and then we have a radius of the circle of 3, so we're going to go 3 spaces to the right, negative 2 plus 3, or 3 spaces to the left, negative 2 minus 3. So in one step we can say that x is going to equal negative 2 plus or minus 3, which has that format of the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac, etc. So here we're starting to see the link between absolute value and distance in one dimension and the quadratic formula. Okay, so we end up, like I said, getting x is equal to negative 2 plus or minus 3, and so x is either equal to, I'm going to write it here, negative 2 minus 3 is negative 5 when y is 0, or negative 2 plus 3, which is 1 when y is equal to 0. And so I'll plot those two x-intercepts, negative 5, 0, or 1, 0. And we can see that we've got 1, 2, 3 spaces to the left of the axis of symmetry, or 1, 2, 3 spaces to the right of the axis of symmetry. Well, indeed, that's exactly what this is saying. We've got negative 2 for the axis of symmetry, 3 to the right, 3 to the left, and voila, we've got a nice link between this working out and the symmetry of the parabola. Okay, that's enough really to sketch the parabola, so we could do that now, but we still want to come up with the other forms of the quadratic equation. Now, if you wanted to come up with points at other heights, you could easily substitute y equal to, let's say, negative 8. If you did that, you would say negative 8 plus 9, let's just write y equals negative 8. Negative 8 plus 9 is equal to x plus 2 all squared. And so here we would have 1. We would take the square root of both sides, and we would be able to work out what x is equal to here. X would be negative 2. Well, let me put 1 equals the absolute value of x plus 2. And so negative 2 plus or minus the distance of 1 would give us the values that we have here. Negative 3 comma negative 8 or negative 1 comma negative 8. So we can use this idea of substituting y with any value and solving for x. Okay, so that's enough for the parabola. We see the shape of the graph and we still need to fill in what's missing, so we need the standard form and the factored form. So to get the standard form, or the function form as I like to call it, we expand. And so we get y plus 9 is equal to, keep in mind this is x plus 2 times x plus 2. And when we expand properly, we get x squared plus 4x plus 4, which gives us y equals x squared plus 4x minus 5. So there's our y-intercept at negative 5. And then we can factor this. And we know we can factor because we had nice, neat whole number x-intercepts. And we can factor as x plus 5 times x minus 1. So we just put those forms in here and make sure that we see the link between the different key features of the graph and the different parameters or non-x and y letters in the equation. So in particular, we're taking a look at the zeros of these. This is x minus root 1, which gives us one root, or x-intercept of negative 5, and then we have x minus root 2. So root 2 is 1, which gives us the second x-intercept of the graph. Okay, right away I'm going to say that the domain is x contained in the reals, and from my standard form I can see that the y-intercept is 0, negative 10. I also know that a is equal to negative 1, which means that the graph is concave down. So I'm going to have a maximum for the vertex, whatever it is, and as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y also goes down because we have that even shape, that x equal to 2 shape. And so we have the same y approaching negative infinity for the left and the right ends. We then need to come up with some values for the x-intercept, so we could try to factor. We could come up with a vertex. So at this point we've got lots of variations on what to do. I'm going to come up with h using negative b over 2a because I have a and b from standard form. So negative times 6 divided by 2 times negative 1 is negative 6 over negative 2, which is positive 3. And now I can work out k as f evaluated at 3, because this is a y-coordinate evaluated for a given x-coordinate. And so negative times open bracket 3 squared plus 6 times 3, and then take away 10 is going to give us negative 9 plus 18 minus 10, and we have 9 minus 10, which is going to be negative 1. So the vertex is located at 3, negative 1, and we know that the graph is concave down. We also have the y-intercept. We have the axis of symmetry now. So we can come up with another mirror image point and go 3 spaces on the other side. We can come up with a second point here. But because the graph is concave down, we're not going to get any x-intercepts. So let's just confirm why that is. When we want to get the x-intercepts, we substitute y equal to 0. And so substituting y equal to 0 gives us negative x squared plus 6x minus 10 equals 0. And I'm going to use the quadratic formula to solve this, but I'm first of all going to multiply both sides of the equation by negative 1. So I like to have my leading coefficient always be positive, wherever possible. So this gives x squared minus 6x plus 10 equal to 0. And from that, the quadratic formula says that x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. And so therefore we can solve for x as negative times b, which is negative times negative 6, which is positive 6, plus or minus the square root of b squared, which is negative 6 in brackets squared, minus 4 times the 1 that I've now come up with, times c, which is positive 10. And that's all divided by 2 times a, which is 2 times 1, which is 2. So we get 6 plus or minus the square root of. Now here we have 36 minus 40, and so the square root of negative 4, all divided by 2. And so this ends up giving us 6 plus or minus 2i, all divided by 2, which is 3 plus or minus I. And so this x-axis is just for real numbers. We can't plot that number anywhere, and therefore we say we have no real roots, or we have no x-intercepts. And so that's why we have none here, so it really fits together with all the rest of the information. Specifically, we'll talk in another video about the quadratic discriminant, but because the quadratic discriminant is negative, therefore we have no x-intercepts. We have no real roots here. Okay, then we need to come up with the range, which we can do now. We know that the maximum y value is going to be at the vertex, which I didn't list yet, 3, negative 1. So the maximum y value is negative 1. So y is going to be less than or equal to negative 1. The axis of symmetry equation is x equal to 3. The factored form is not applicable because we don't have real x-intercepts. We only have complex roots for the quadratic equation. And then the vertex form, we simply need to substitute h, k, and the original value for a. So when we substitute those in, we have a equals negative 1, h equal to 3, and k equal to negative 1. So I'm just going to write that information up here in one step. We're going to get y minus k, which is y plus 1. Maybe I'll write the vertex form here. And so we've got a lot of sign changes. Be careful of that. Y minus negative 1 is y plus 1 equals the a value of negative 1. I'm just going to write it as a negative times, and then x minus 3 for the x-coordinate of the vertex. And don't forget the exponent of 2. Now, we could come up with some other points on the parabola because we don't really have enough to come up with a sketch. Here's an opportunity for us to substitute a different height in for y other than y equal to 0. If we were to substitute negative 2 in for y, we might be able to solve the quadratic equation. Let's try it. Let's solve for x when y is equal to negative 2. So doing that would give us negative 2 equals negative x squared plus 6x minus 10, and I'm going to take everything to the left side set equal to 0. So we'll get x squared minus 6x, negative 2 plus 10 is plus 8. And then this, if we want to see if it can factor, we end up getting x minus 2 times x minus 4 equal to 0. So that actually gives us two x coordinates of positive 2 or positive 4 when y is equal to negative 2. So positive 2, negative 2, or positive 4, negative 4. We could pick another set of points, but this will be enough to give us a bit of the shape. And we have a parabola. Maybe I needed more points because that's not looking so smooth, but the graph looks like that. So don't be shy to pick other y coordinates and see how you might be able to come up with x values to help you come up with the shape a bit better. I'm going to take another look at the standard form from question number 3 and convert it directly into vertex form by the method of completing the square. Now, if you need to revise the completing the square method, check out the video on completing the square. So we are going to be adding and subtracting just the right number so we can convert the first two terms into a binomial squared. So the first thing I've done is factored the a value, which is negative 1, only out of the x squared and the x, the quadratic and the linear terms. I didn't factor it out of the constant. And so I need to find the number which is half of negative 6, and then I need to square it. So half of negative 6 is 9, so I'm going to add 9 and subtract 9, which means I've actually added 0. So my new version of the equation is equivalent to the original equation. And what that allows me to do is to take the three terms x squared minus 6x plus 9 and write it as a binomial squared. And then I still have minus 9, and then I still have minus 10 outside. And so the x squared minus 6x plus 9 factors into x minus 3. So now I really have a 1 times that bracket minus 9 inside the square brackets, which needs to be multiplied by the negative 1 in front. So I get y equals negative times x minus 3 all squared. Negative 1 times negative 9 is positive 9, but this negative 10 is not inside the square brackets to be multiplied by negative 1, so we don't actually change the negative 10. And so we end up getting y equals negative times x minus 3 quantity squared plus 9 minus 10 is negative 1. And I like to rewrite so my transformations are on the same side as the variable that they affect. And from here we can see that the vertex or the h, k values are positive 3 and then -1. So that confirms what we did in the previous question when we used the formula h equals -b over 2a, and we got a +3, and then we worked out k by substituting the x-coordinate into the function, and we got y equals -1. So this is an alternative approach to go directly from the standard form to the vertex form without using this formula. Here in number 4 we have the factored form, so I'm just going to fill in as much information as I can straight away. We have the x-intercepts are located at -2, 0 or at 4, 0. And from the a value being equal to -1/2, we know that the graph is going to be concave down. So we know that the vertex will be a maximum point. We don't know exactly where yet, but we also know the left and the right end behaviors. As x approaches -infinity, y will go down, so approach -infinity, and the same on the right-hand side. Then we can come up with the standard form by expanding. I'm going to come up with the h value by finding the midpoint of the two x-intercepts. So -2 plus 4 divided by 2 is going to give me 2 over 2, which is 1, and therefore k is going to be f of 1, which is -1/2 times 1 plus 2 times 1 minus 4, which is -3. So here we have -1/2 times -9, which is +9 over 2. So the vertex is located at 1, 9/2, and it's going to be a maximum, and therefore the axis of symmetry equation is x equal to 1. We can come up with the y-intercept by substituting x equal to 0. Now it doesn't have to be done in the expanded form. I can use the factored form to solve for y. So y equals -1/2 times 0 plus 2 times 0 minus 4. 2 divided by 2 is 1, and negative times -4 is +4. So the y-intercept is located at 0, 4. So we can also come up with the range. The graph is concave down, so we have a maximum y-coordinate of 9 over 2, so y will be less than or equal to 4.5, 9 over 2. We'll also put the vertex in, the vertex form rather, so I know a is equal to -1/2, h is equal to 1, and k is equal to 9 over 2. So the vertex form again is y minus k equals a times x minus h all squared. So I'll just put the answer up here for the vertex form. Y minus 9 over 2 equals -1/2 times x minus 1 in brackets squared. And then the last thing apart from the sketch is the standard form, so I'm just going to expand the factored form. You could also expand the vertex form, but I think for me I'd rather do it with the factored form. And I'm going to save the multiplying -1/2 to the very end. So I'm going to multiply the two brackets together first. We get x times x, which is x squared, then minus 4x plus 2x minus 8, which is -1/2 times x squared minus 2x minus 8, which is -1/2 x squared plus x plus 4. And we should be able to confirm some other information, like the y-intercept here. In particular, if x is equal to 0, y is 4, so we have 0, 4. So we've got all the information, we just need to plot the points and then sketch the parabola. We can also come up with the midpoint. The vertex is at 1, 9/2, which is 1, 4.5. Plotting the axis of symmetry, we can come up with the symmetrical point on the other side from the y-intercept. So from here we can sketch our parabola, and the value of a being 1/2, or -1/2 I should say, tells us that this parabola is going to be a little bit shorter and therefore wider looking than the parent graph of y equal to x squared. You could also expand, get the standard form, and then from standard form you could complete the square to get the vertex form. So there's lots of ways that you should be able to move forwards and backwards between the different forms and coming up with the different information about the parabola. In number 5 we're given factored form, but not factored form where the a has completely been a common factor. So I'm first going to come up with, well, let's say the domain, which is straightforward. And the value of a, because this is going to be expanded as 6x squared plus other things, I know that a is equal to 6, and so I have concave up. So I'm going to have a minimum, and I know my end behavior, y will approach positive infinity on both the left and the right ends. Might as well continue expanding to get the standard form, so we will have 6x squared minus 8x plus 3x minus 4, and so the standard form, I'm just going to simplify it over here, is y equals 6x squared minus 5x minus 4. So right away I know the y-intercept is 0, negative 4. Now I could have gotten the y-intercept by substituting x equal to 0 from factored form as well. So just to see how that would work, I would get y equals 1 times negative 4, because 0 plus 1 is 1, which gives me negative 4 again. Okay, so a couple of ways of confirming that information. That's great. I can also come up with the x-intercepts from the factored form by setting y equal to 0. And so doing that gives me either the first factor or the second factor equal to 0, and that's going to give me x-intercepts that are fractions. So x is either equal to negative 1/2 or x is equal to positive 4/3. So I can record my x-intercepts here, and then I can use the midpoint of those two x-intercepts to come up with the value for h. So I can call the x-intercepts r1 and r2, and to get the midpoint we add those values together and divide by 2. So negative 1/2 plus 4/3 divided by 2, which I can say is actually 1/2 times. So 1/2 times the numerator. So before multiplying the 1/2 through, I'm going to get a common denominator, which is going to be 6. So negative 3 over 6 plus 8 over 6 gives me 5 over 6, and then half of 5 over 6 is going to be 5 over 12. So a bit of a messy number to work with, but we can still substitute into either the expanded standard form or the factored form. So I'm going to work out k as f of 5 over 12. I think I'll still put it into the factored form. So I'm going to get 2 times 5 over 12, which is 5 over 6. And so 5 over 6 plus 1 times 3 times 5 over 12, which is 3 times 5 over 3 times 4. So that's 5 over 4, and then take away 4. And then getting a common denominator between those two brackets. I'm going to get 11/6 and then 5/4 minus 16/4. We get 11 over 6 multiplied by negative 11 over 4, which is negative 121 over 24. And so we have a vertex located at 5/12, comma, negative 121 over 24. And if we approximate that number, well, this is a little less than 1/2, and this is a little bit smaller than negative 5. So we're going to get 1/2, comma, negative 5 approximately for our vertex. And we have negative 1/2 as well as 4/3 for our x-intercepts. So it's awkward to sketch here. We have an axis of symmetry coming through the vertex. It's not quite straight, so use a straight edge for your axis of symmetry for all lines. And just when I want to buy myself some time, something easy to do, I label all the axes. So I've got my vertex, I've got my two x-intercepts, and the y-intercept is located at 0, negative 4. At least that makes sense because it's along the same general path, and my y-intercept has a mirror image point 5/12 on the other side, which is actually probably inside the 1 value. Okay, so then I have enough points to plot the parabola. It's a bit tight, but we can make sure to curve it. We can talk about, we've got the end behavior. Let's see what else we're missing. We need the range, so we know that y is going to be greater than or equal to negative 121 divided by 4. We have the vertex form because we know the value for a, h, and k, so the vertex form is y minus k equals a times x minus h all squared, which is going to be y minus negative, or y plus, 121 over 24, equal to the value of a, which is 6 times x minus the value for h, which is 5/12. And then don't forget to square, because without squaring this, we would have the point slope form of a line as opposed to the vertex form of a parabola. The point-slope form and the vertex form are both examples of transformational forms. The last thing to do then is just to fill in the blanks here and here. We saw the factored form is written as y equals a times x minus the first root, or x-intercept, times x minus the second root, or x-intercept. Now we see that this factored form doesn't really lend itself to having the a factored out front, but we can do that, and we just have fractions for the x-intercepts here and here. So the first x-intercept is at negative 1/2, so x minus a negative 1/2 is x plus 1/2. The second x-intercept is at positive 4/3, so x minus 4/3 is x minus 4/3 directly. So if we were to expand this, we would be sure to get the same standard form. Now, you should be able to go directly from standard to vertex form by completing the square, and that's something to practice so that you have all the quadratic algebra kind of working in a really flexible, fluid way. Here in number 6, we have the vertex form of the parabola, so let's fill in the things that are quick and easy for us to do. The domain is all real numbers, and the vertex is located at negative 5/2, comma, negative 25/4, which is negative 2.5 and negative 6 1/4. So negative 6 and a bit would be right around here. And then we have that a is equal to 1, and so the parabola is concave up. We have not vertically reflected the parent graph, which means that as x approaches negative infinity or positive infinity, y goes in the same direction, which is up. Y approaches positive infinity. We have the axis of symmetry equation, which is x equals negative 5/2, and we have that the range is going to be y is greater than or equal to the y-coordinate of the vertex, negative 25/4. And we also have that the vertex is a minimum. Okay, now let's get the y-intercept, which straightforwardly we just substitute x equal to 0 from the given equation form. So y plus 25/4 is equal to 0 plus 5/2 in brackets squared. And it turns out that 5/2 all squared is 25/4, so we end up getting that y is equal to 0. So we have the y-intercept at 0, 0, and because when x is 0, y is 0, we also have when y is 0, x is 0. So we have an x-intercept at the origin as well. And we could come up with the other x-intercept if we wanted to by symmetry through the axis of symmetry. We just go 2.5 spaces on the other side. So half, 1, 2, and we should get that the other x-intercept is at negative 5, 0. Let's put it in, but let's confirm it by solving. And so to get the x-intercepts, we substitute y equal to 0. Now, we could expand this first and get the standard, we could factor, or we could just work directly from the vertex form, which is what I'm going to do. If I substitute 0 for y, I get 25/4 is equal to x plus 5/2 all squared. And this method of solving is really nice because we only have x showing up one time in the equation, so we just take square roots on both sides. Now, being really careful, we know that the square root of 25/4 is only one answer, which is 5/2. And then the square root of stuff squared is the absolute value of that stuff. So we get absolute value of x plus 5/2. And now we could use this distance model, this circle model, where we've got a center located at negative 5/2. That's coming from here. And then we go right or left the radius, which is this number. So negative 5/2 to the right by the radius takes us to 0, or negative 5/2 and then decreasing by the amount of the radius takes us to negative 2.5 minus 2.5, which is negative 5. So indeed, we're getting x equals negative 5/2 plus or minus the radius distance. And so x is either equal to negative 5 or 0. So those are our two x-intercepts, and we can come up with the factored form and the standard or expanded form. I'm going to expand first, and then from the expanded form I'm going to factor. So to expand, we get y plus 25/4 is equal to x squared plus, we multiply these two terms together, and then we double because there will be two of them when we expand. And so that gives us 5x, and then we square the last term, which gives us 25/4, and the 25/4s are the same as what happened here. They give us 0, and so we get y equals x squared plus 5x. So our factored form will be easy to come up with because we don't have a constant term. Because we don't have a constant term, we can just take our common factor of x from both terms on the right-hand side. So we factor out an x, and so we get x times x plus 5. And this is why when we substituted y equal to 0 to get the x-intercepts over here, we ended up getting either x equals 0 or x plus 5 equals 0, which gave us x equals 0 or x equals negative 5. So the same two roots that we got using the taking square roots way of solving from the vertex form. So we've got lots of different ways of playing around with quadratics. I'm also going to plot the y-intercept, which we've done. So we don't have points at 3 different heights. You might want to come up with another y-coordinate, or you might just hope for the best when you're sketching the parabola, because working with fractions might make it a little bit harder to substitute nice values for y. But we basically get the parabola shape like this, and don't forget to label and put arrows on the ends of the axes. And you can also label the axis of symmetry with its equation, x equals negative 5 over 2. So that should be everything that you need to know about the quadratic algebra. If you need some work with quadratic discriminant, factoring, completing the square, or other quadratic word problems, take a look at some of the other quadratic videos. That's all for now. Thanks for checking out Raylene Maths.